Hey everyone. So here we're going to talk about function transformations today. So I think a great place to start is, well, what even are function transformations? So I think the first thing that comes to mind is when you're given a complicated function, sometimes it can be easier to just think of, well, how does this compare to an easier function? So then we can think about how it deviates from an easier function instead of trying to understand it completely on its own. So again, if we start with a function that looks a bit easier, we usually call these as parent functions. These parent functions can give us some insights about what these complicated functions might look like and how these functions deviate from these parent functions. Today we're going to talk about 5 different types of transformations. The last one, you'll see I kind of cheat. This is like 2 different types. But what I want folks to check out first is that there's kind of 2 different parts to transformations. We either say they're a vertical transformation or they're a horizontal transformation. And then we're also dealing with either shifts or stretches. So keep an eye out for similarities between these different types of transformations. All right, so before we get started, I quickly want to talk about parent functions. So here, today, the parent function I'm going to use most is x squared. So like I mentioned earlier, when we're looking at these complicated functions, sometimes it's easier just to see how they deviate from a familiar function. So this is the familiar function that I'm going to be referring to. And I also want to give a quick shout out to Desmos. So this is a free tool that anyone can use online, and you can make these really cool graphs. So I'd suggest it to anyone that's learning about function transformations to go play around in Desmos. So for a vertical shift, what we're doing is we're taking each point on our parent function and we're moving it up 1 unit. So each and every point, we're shifting it up exactly 1 unit. So here, I think it's really helpful to look at what happens to a single x value. So here we have an x value of 0. In our parent function, we have the point 0, 0. So now this function transformation is saying, okay, add 1 unit to every output. So again, think about this as some f of x, and think of this as some function plus 1. So take every output and add 1 to it. So again, having an output of 0 here, we're going to be adding 1. That's kind of boring. So let's check out the point 1, 1. So that's in our parent function. So we'll look at the output and we're going to add 1 to it. So for the same input in our parent function, we'll keep the 1 and add 1 to the output. Let's just try one more. Again, up here, we have the point -2, 4. We'll keep the -2, but add 1 to the output, and that's 5. So again, I think when we're talking about transformations, it can be helpful to think about inputs and outputs. So any sort of vertical transformation changes outputs. So just to give another quick example here, if we're looking at a single point, so keep the inputs the same, what this complicated function is saying is, okay, take the function that you started with, take each output and subtract 3. So take the output that we had 0 and subtract 3. So we're taking each point, keep the input the same, but shove the output down 3 units. So again, we're just sliding everything down 3 units. All right, so enough of all my lines there, but I hope that makes sense. Next, we're going to talk about horizontal shifts. So I feel like horizontal transformations are a bit trickier than some of the vertical ones. So here, with horizontal shifts, instead of moving a function up or down, now we're going to be moving a function left or right. So one thing that I want to point out is that previously, for vertical transformations, we would be adding or subtracting outside of the function itself. Here, notice that we're actually adding or subtracting inside the function. So that's one way to distinguish between a horizontal shift or a vertical shift. So to show a quick example here, we have x plus 1 quantity squared. So look what that's doing. We're taking a single point, so I'm looking at the vertex here, 0, 0, and we're shifting it to the left 1 unit. So it might be counterintuitive at first, like, wait a second, we're adding 1. Shouldn't that send our graph to the right? Think what happens though. So if we do have x plus 1 squared, well, what value do we need to plug in for x in order to get out 0? So if we plug in -1, see how we get 0? So this is how we know that we have the point -1, 0 on our graph. And again, we can have shifts to the right. So if we're thinking about points on this graph, what happens if we plug in 3? Well, we get out 0. So I guess in my head, the way that I think about it is that if we're subtracting a number inside the parentheses here, then we need to have a higher input to kind of counterbalance that. In any case, if I can kind of summarize horizontal shifts, if we have a parent function, y equals f of x, and we have a transformation, f of x plus a, if a is greater than 0, so we're adding a positive number here, that's going to shift our graph to the left. Or if we're subtracting a number, or adding a negative number, that's going to move us to the right. So just to quickly look at a single point here. So here we have the point 1, 1. Notice how this is shifted over 3 units. So we have 4, 1. So again, the outputs are still the same, but we're shifting the inputs over 3 units. So again, the basic structure of the graph is going to look exactly the same. We're just sliding it over left or right. So it's just like the vertical shifts. where again, the structure itself looks exactly the same. We're just sliding it up or we're sliding it down. But that's going to change a little bit when we talk about stretches. So here, for example, I'm sticking with our parent function, x squared. So think about this as f of x. Now, a vertical stretch is going to look like 2 times f of x. So we're multiplying the function by a value on the outside. So if we look at a single value here, so let's look at 0.11. What this new rule is telling us here is that we're taking each output and we're multiplying it by 2. So again, think of f of x as your output. So see how nothing is really changing the input? So we're having 2 times the output. So here, on our transformation, the input isn't changing, but we're multiplying the output by 2. So just to go over another example. Here we have the point -2, 4. So looking at our transformed function, we have -2, 8. Right? So we multiplied the output by 2. But look what happens if we have a vertical stretch by a value less than 1. So instead of the graph getting really skinny like you saw last time, so on the left side we saw something like that. That's a really bad parabola, forgive me. So here, if we're looking at, again, the point -2, 4, now our new output is -2, 2. So again, whenever you see a vertical transformation, you're impacting the outputs. So now let's talk about horizontal stretches. All right, so here we're keeping the same parent function, f of x. But now if you look at what transformation we have, we're actually multiplying by 2 inside the parentheses. So if we look at what happens with this function transformation, we're actually squishing in this new function. So you can think about this as a compression. So if we look at a single point on our original graph, let's say 2, 4. Now it only takes half the time to get to this height, 1, 4. So to me, it's going to sound silly, but I think about time. So I think about, oh wow, these inputs are now moving twice as fast as before. So now, instead of it taking 2 units to get to a height of 4, it only takes 1 unit. So Desmos has this really cool option to input the domain of a function. So here, I entered the domain of the original function as -2 to 2, including -2 and 2. And then for our transformed function, -1 to 1. So the reason why I wanted to show folks this is because since we're multiplying by 2 on the inside, see how it only took half the time? I know that's kind of a silly analogy. To go through the same outputs. So again, the way that I think of it is if you have some function where you're multiplying on the inside by a value greater than 0, greater than 1, that's going to compress your function. But see here, now we have a case where a is less than 1. See how now it takes twice the amount of time to get to the same outputs? So what do I mean by that? If you look again at our point 2, 4, well, now it takes 4 units to get to that same height. All right. So again, it's taking twice as long as it was before. So if I can kind of summarize this, if a is less than 1, we're looking at a stretch. And if a is greater than 1, we're looking at a compression. So now I'm going to quickly talk about reflections. These are kind of fun. Again, I want to show folks that this change is happening outside the function. So this is just a reflection over the x-axis. One way to think about this is taking each value, each y value, and just multiplying it by a negative. So instead of having a 0.24, we'll have a 0.2, -4. All right, so take each output and just multiply it by a negative. And we can't really see horizontal reflections with this parent function. The reason why is because f of negative x is just equal to f of x. So again, negative x squared is just the same as x squared. So these two functions are going to overlap. So if you'll allow me to give you a better example, if you look at y equals x plus 1, a horizontal reflection instead of f of x looks like f of negative x. So again, if we look at a point, here we have a point 2, 3. So on our new graph, on our transformation here, we're going to have the same output. We're just multiplying the input by a negative. So to summarize all the different transformations that we talked about today, we talked about vertical shifts. So if a is greater than 0, we're just sliding our function up. If a is less than 0, we're sliding it down. For horizontal shifts, this was the one that was kind of backwards. So if a was greater than 0, we're sliding the function to the left. And if a is less than 0, we're sliding it to the right. Vertical stretches, again, you're taking each output and you're just multiplying it by the same number. So this either kind of made our graph skinnier or wider. But it's pretty intuitive as far as what the graph would look like. Whereas horizontal stretches, on the other hand, to me, I think is a bit trickier. So remember that if a is greater than 0, this compresses the function. If a is less than 0, this stretches it or widens it. And then we talked about reflections. So the cool thing is that we can actually combine a lot of these different transformations too. So don't feel that we're limited to just a single transformation. So just to give a quick example, here we're starting with our same parent function. Now look at all these different transformations. So we have a vertical stretch, we have a horizontal shift, and then a vertical shift. So I'm going to think about that horizontal shift first. And then after that, I usually like thinking about, well, what impacts the function first? So order of operations tells us that we're going to multiply before we add or subtract. So we're going to have the vertical stretch. And then a vertical shift. So again, this is just one example. Transformations you can do a lot of really cool different things with, but I hope that this gives you enough information to get started. Thanks for watching.